Hello! In this video, we're going to talk about how do we recognize, describe, and find domains and ranges of functions. So we're going to cover some topics that were covered in Algebra 2 and just hit them again. Domain and range from a graph, set, interval, and inequality notation, and implied domain. Let's get going. All right, domain and range. Remember that domain are all the x values that are included, and the range is all of the y values that are included. So in interval notation, we see that the domain from left to right starts here at -6, and -6 is included. Because it's included, we put the -6 in a bracket. And so as we're traveling along, all these x values are included until we get to 0, where there's a hole. To represent that hole, we put this 0 with the parentheses, saying you can get really, really close to 0, but you can't touch it. And then just on the other side of 0, the graph starts again. So we union to where the graph starts again, just on the other side of 0, and it goes off forever. So we say it goes to infinity. And infinity needs a parentheses because you can't actually ever get there. All right, now for range, we look at the lowest y value, which the lowest y value included is -6. And so now we have to check, are there any interruptions in the range? And you might be thinking about this hole here, but you can see that -3 is included in the range because it's part of the function over here. So the range actually doesn't stop and goes off to infinity. All right, so now as we head to inequality and set builder, let's make a quick little note here. Anytime your less thans or greater thans have the or equal to, you're going to put a bracket. If it's strictly less than or greater than, we're going to put parentheses. And anytime you see that U, which stands for union, we're going to write or. All right, so now we can do it. All right, for the inequality notation, because we had this U, I have the or, and I'm going to write out each of these things. So I like to write from left to right. -6 is less than or equal to x, which is less than 0. What that means is that all of these x's right here, look at them, -1, -2, they're all between -6 and 0, but 0 is not included. Or, a lot of people want to write x is greater than 0, which is what this says, but just reading from left to right, 0 is less than all of these x's. So the range, since it goes from -6 to infinity, -6 is less than or equal to all of the y values that are included. All right, so what may be new to you is set builder notation. And the only difference between this and inequality notation is that you have to define it as a set. To do that, we use these little brackets, which I can't draw very well. But it's the domain of all of the x's such that, this little bar means such that, and then just write out exactly what we wrote out for inequality notation. And remember to close that bracket. The y's, exactly the same thing. It's the set of all y's such that -6 is less than or equal to y. All right, here's a graph. Why don't you give it a try, writing it in all three notations. Pause the video, and then we'll come back in a second. So pause in 3, 2, 1. All right, so the domains we should have got was -infinity to -5, both in parentheses, then 4 to infinity, and 4 has a bracket. The range is 0 to infinity because here 0 is included in the range, even though it's not right here. So the domains, reading from left to right, all these x's are less than -5, or all these x's are greater than 4, or greater than or equal to 4. You could also write that as 4 is less than or equal to x. And all of these y's are greater than or equal to 0. You could have also written 0 is less than or equal to y. To make this into set notation, we're just going to put the set of all x's such that, and close our set, or the set of all y's such that y is greater than or equal to 0. And just as a reminder, if we have domains that are -infinity to infinity, we can, in other notations, we can just draw this little r with the two backs that stands for all real numbers. All right, now let's talk about what it actually means to be a function. So to understand functions, we first need to understand what a relation is. A relation is a rule that relates or pairs the elements in set A with the elements in set B. What does that mean? That just means that there's some rule that says, like, if I give you this input, I'm going to get a certain output. Now, a function is a relation that assigns each element in A to exactly one element in B. So this element right here could not go here and here. In other words, what we're trying to say is each input has exactly one output. So this input right here in A cannot go to more than one place in B. It can only go to its single output. It cannot go to another one. On a graph, you can test this using the vertical line test. If you can move a vertical line through a graph and it doesn't hit the graph in more than one spot, then it is a function. But if you can move it through the graph and it's hitting in more than one spot, that means that this input, this x value, has multiple outputs. See, those are two different y values for the same x. So this means this is not a function. Take a second to pause the video and think, which of these, number 1 or 2, is a function? Which input would have only exactly one output? Account balance to bank account number, or bank account number to account balance? Well, I hope you chose number 2, because a bank account number would only have one exact output of that bank account's balance. Whereas multiple people could have the same account balance, so it would not map back to one single bank account number. Lastly, we're going to look at implied domain. So there are a few things that you have to look out for whenever you're finding domain algebraically. You know that you cannot divide by 0, and you cannot take the square root of a negative. So we're going to use those rules to find domain. We're going to start by finding the domain of 3 plus x divided by x squared minus 6x. So we see that x is in a denominator here, so we need to figure out when would x equal 0, and that cannot be in the domain. So we're going to set this denominator equal to 0 and solve for x. And we see that whenever x equals 0 and x equals 6, that causes this denominator to equal 0. So the domain is going to be all real numbers except x is equal to 0 and x is equal to 6. And hopefully you remember whenever you divide by 0, you're creating asymptotes, and that's what's interrupting the domain. If you'd like to see that, you could go to desmos.com and type this into the graphing calculator and look at the graph. Look at what happens at 0 and 6. All right, in our last example, even though there are more types of these, we have 2x divided by the square root of x minus 9. Now we know that we cannot take the square root of a negative. So typically what we would do is just take x minus 9 and set it greater than or equal to 0, because that represents all of the non-negative numbers. But because this is in a denominator, this cannot be equal to 0. So this does not include this or equal to right here. It's strictly x minus 9 is greater than 0. So my domain is x is greater than 9. Now, what trips up a lot of people here is that the last example that we did, that told us what wasn't in the domain, whereas whenever we have square roots, our answer is the domain. So be sure to look out for that. All right, and that's everything. Goodbye.